All right, so we left off looking at what are the properties, what are the features of the anatomical makeup of muscle, and what are the ways that we can influence how much force a muscle generates. In other words, how much load that muscle can overcome. How can we increase that? And so we talked about some other factors previously. So we would have introduced this idea of isometric versus isotonic contractions. We would have talked about the number of cross-bridge cycles, right? So that is how we increase force generation, by having more active cross-bridge cycles. And we would have also talked about this idea of summation and trap. So trap, we said, was this natural inherent property of the muscle where when you stimulate it once, you allow it to fully relax. The next time you stimulate it, it somehow generates more force until it gets to its peak amount of force generation. Mechanism, not entirely clear, but we do know that is a phenomenon that we see with muscle. Summation, we also talked about, if we increase the frequency, we would see the same type of increase in force generation. But this phenomenon was more explainable. We can actually rationalize this. Because there was not full relaxation, so jumping back here, because the muscle did not fully relax each time, we are starting from a place of the sarcoplasm already having calcium in it. And so the next time we stimulate, it'll just be stronger because we already have the machinery warmed up, right? The latent period is going to be negligible because we're already warmed up. Calcium is already in the sarcoplasm, and so we can generate more force with a subsequent stimulation. So those are some ways that we could generate more force. We're going to talk about some other factors going forward, but we want to explain how these factors are relevant. So when you think about the fiber diameter, that's the size of a single muscle fiber. That is going to dictate how much force the muscle can generate, right? The force generating capacity is the inherent ability of the muscle to generate a set amount of force. That is going to be determined by the number of cross bridges, which we kind of talked about before. So if we have more actin and myosin interactions caused by more calcium, we can have more force being generated. And so there are two ways that we want to think about this. If we have more cross bridges per sarcomere, we're going to have more force. But if we have more sarcomeres in parallel, remember within a single muscle fiber, we've got lots of myofibrils. On each of those myofibrils, we have several different sarcomeres. So if we have more cross bridges, that's more force. But if we also have more sarcomeres in parallel, that is also more force. What is constant? So what remains constant and unchanged is the number of thin and thick filaments per sarcomere. So we can't increase the actin and myosin on a single sarcomere. What we can do is kind of jam more sarcomeres in there, and we can do that by jamming more myofibrils in a muscle fiber, okay? We also cannot increase the number of muscle fibers. What we do is make them bigger by putting more myofibrils in. And this is what happens when you go to the gym, you're working out, you're lifting heavy weights, you're bulking up your muscle. You are increasing more cross-bridge cycles by way of increasing more sarcomeres, and you increase more sarcomeres by putting more myofibrils in a single muscle fiber. So the number of fibers is constant, and the number of thin and thick filaments on a single sarcomere is constant. But what we can do is put some more myofibrils in, and that's what happens when you lift heavy weights and you increase the diameter of a fiber by putting more myofibrils in. Okay, and that way, when you bulk up those muscles, they can generate more force, they can lift heavier loads because there's more cross-bridge cycles happening. All right. Another thing we can change about the muscle is the length, right? This is another way that we can increase how much force is generated. So muscle fibers are usually at an optimal length. And there's a specific length that the muscle wants to be at in order to generate the maximum amount of force that is possible for that muscle. That is what the optimal length is. Typically, the resting length is, that's how we can give the most amount of tension. So a muscle in its resting state, it's being suspended across a joint, usually by two bones, right? An origin point and insertion point. And at that length, that is the optimal length that will give us the maximum amount of force that is allowed for that single muscle. That's because we're going to see the maximum amount of thin and thick filament interaction, or actin and myosin interaction, or cross-bridge cycles. Okay. Now in situ just means the way that it is in the body naturally. Most muscles, again, are suspended at their optimal length. That is why they are suspended, right? They're not just flopping around in the body. They're being held with some a bit of tension by being attached to a proximal end and then a distal end to keep them at that optimal length. So let's talk about what the optimal length looks like, and then what some non-optimal lengths will look like as well. So if we have a length that is greater than optimum, we're going to decrease the amount of cross-bridge interaction. Okay, think about this sarcomere over here, right? It's really stretched out. The fibers, the actin filaments, the actin and myosin are really far away from each other. And so when this sarcomere starts to shorten, we're not going to see as much cross-bridge cycling because we're starting with it in such a stretched out, expanded state because it is at a length that is greater than its optimal length. Okay, and so when this sarcomere would contract, this is the amount of force that it would generate, right? We can see the percent of maximum tension here. And so of its full potential, it's only going to generate a small amount of the full maximum potential that is possible for this muscle. Here is another scenario of being greater than optimal length. And while it's a little bit better than this scenario here, it is still larger, it's still more stretched out, it's still greater than that nice optimum resting length that we'd like the muscle to be at. So when this sarcomere contracts, it's only going to generate about 50% of the maximum tension that is possible for this muscle, which is not 100, right? It's not the best, it's not the most ideal. Contrasting that to a muscle that is at less than its optimal length, right? This is where the thin and thick filaments overlap so tightly. There's too much overlapping. We need for there to be room for comfortable cross-bridge cycling. And so when the Z lines are so close together, we're pretty much starting with the sarcomere in this tightly contracted state. And so there's no opportunity for the shortening of the sarcomere because there's that maximum overlap already taking place. This is also not going to generate the maximum amount of tension that is possible for this muscle. So again, we're seeing that this very contracted, very shortened sarcomere is less than its optimal length. And if that were to contract, we would only generate about 50% or so of the maximum tension that's possible for the muscle. And this green area here, so this is kind of the sweet spot. This is the optimal length, kind of the ideal length that the muscle needs to be at. And this is how muscles are when they are suspended naturally in the body. They're at their optimal length, unless you've got maybe your limbs in a difficult position where you're either stretching that sarcomere out or contracting that sarcomere too tightly. But typically, in the body, the muscles are at their optimal length, and they will generate 100% of the maximum tension that is possible for that muscle. And what we can see here is the sarcomere starts out not too contracted, but not too stretched out either. And when it is allowed to shorten, let's go here. When it is allowed to shorten, it is just the right amount of space to give the right amount of overlap, to give us the maximum amount of cross-bridge cycling, to give us the maximum amount of tension production, okay? And this is what we mean by the optimal length. Okay. Let's talk about how we regulate force generation. So let's just kind of recap the things that we said here. So we said that the fiber length was one factor that affects force generation. The fiber diameter, so putting more myofibrils, was another thing that affects force generation. And then from our previous discussion would have been the frequency of stimulation is a third way that we can increase force generation. Let's talk about how we regulate force generation. How do we change it, right? So we talked about the factors that will increase it, but how can we manipulate that? So if we want more force generated, we're going to need to call on more fibers. And I introduced this idea the last time that when a muscle is contracting, if I'm lifting a piece of paper, which is relatively light, I'm not actually using all the fibers in my biceps, for example. And so this idea of recruitment is that in order to generate more force, I can simply call on more fibers, right? Hey guys, let's kind of pitch in, and you can increase the force generation by calling or recruiting more fibers to start contracting. Okay, so the muscle, we said, is a bundle of many muscle fibers, right? The fibers are synonymous with the single functional units, the single cells inside that muscle. And so not all of them are actively contracting each time the muscle contracts. So if we call on or recruit more fibers to contract, we then have more cross-bridge cycling and we can have more overall force generation or tension production. Okay. Now, recruitment can occur at many different levels of the motor unit, and we'll talk about that coming up. So here is a review of what a motor unit looks like. So it's the motor neuron and all of the fibers that it is innervating, excuse me. So this is what one motor unit X looks like. This is what another motor unit Y looks like. So within a muscle group, we have several different motor units being innervated by different motor neurons, right? Let's say I'm lifting a light object. I may only need to have 5 fibers actively contracting. So I would only have innervation or stimulation of motor neuron X to motor unit X alone. Okay, if I wanted to increase that, lift a heavier object, like let's say a water bottle, for example, I would need to recruit or call on some additional motor units and their additional associated fibers. So I would recruit motor unit Y. It's got more fibers associated with it. It's going to help bring about more cross-bridge cycling. And so now I have motor unit X contracting along with motor unit Y, and now I have much more force generation because I've got much more fibers contracting and they're providing much more cross-bridge cycling, which is how I'm getting more tension. Okay, and that's what recruitment is. We can call on additional motor units which are associated with additional fibers to bring about additional cross-bridge cycling. Now, motor unit recruitment happens in a specific principle. We're gonna call on or activate motor neurons that are smaller first, and then we're gonna call on or activate motor neurons that are larger last. So essentially we have a motor neuron activating a bunch of fibers, right? And usually we have a small motor neuron, which is a thinner diameter in terms of that neuron, attached to a smaller amount of fibers. The fibers also have a smaller diameter, right? And so those types of motor units are usually used for delicate movements. Again, lifting maybe something light, a piece of paper, touching your fingers, touching your eyes, right? The smaller muscles of the body, blinking, moving your toes. Those smaller, more delicate or fine touch movements are typically associated with smaller motor units. And again, smaller motor units have neurons with smaller diameters. They are attached to a smaller number of motor fibers or muscle fibers. And then the muscle fibers also have smaller diameters. So everything is kind of smaller for more fine touch, delicate, smaller movements. Contrasting that to larger motor units. These are usually found where we have the neurons with larger diameters. We'll talk about the sciatic nerve. coming up in our lab this afternoon, and it's a very thick nerve. It's a very thick nerve, and it has larger amounts of fibers attached to it. And the fibers themselves are bigger muscle groups. They've got bigger diameters. And these larger motor units are usually associated with muscles that are being used for strength. So think about the quads, think about the hamstrings, think about the gastrocnemius. Those larger, more bulky muscles, are usually used for strength and are usually attached to larger motor units. Okay. So that's what I think. I kind of may have jumped ahead of myself here. So basically we've got the size of the motor unit varies. So small units are for delicate movements. Large units are for strenuous movements or for strength. And so the fiber diameter is also going to vary with the motor unit as well. So when we talk about the size of the motor unit, remember, this is speaking about the number of fibers attached. That's small as well. But then the fiber diameter, the size of the fibers that are attached, are also small as well. And again, we're going to see small fiber diameters for weaker movements, and then larger fiber diameters are for stronger movements, for strength, for posture even, such as the soleus muscle of the legs and calves. All right, let's talk about the relation here of the motor units, just kind of reiterating this idea that a smaller motor unit has smaller fibers. The neuron of the motor neuron is going to be small. It's going to have a smaller cell body, and it's also going to have a smaller axon diameter. The larger motor units are going to be attached to larger fibers. The somas of these neurons are going to be larger. The axon diameter of these neurons are also going to be larger. So kind of just reiterating what I explained before. A motor unit being smaller, associated with finer, more delicate movements, means that the neuron is smaller, the soma of that neuron is smaller, the diameter of that axon is smaller, the fibers attached are smaller, and then there are less fibers attached as well. Contrary, we have larger motor units associated with larger, more strenuous or postural function. That's going to have larger axon diameters, larger cell bodies, a larger number of fibers attached, and then larger fiber diameters. Okay. All right, now let's get to the size principle. So this is the order in which we recruit muscle for force generation. The order in which we recruit additional motor units, that is. So we always recruit small units first, and we recruit large units last, right? Larger units have larger neurons attached to them. They're going to be harder to depolarize to threshold because they're bigger neurons, bigger cell bodies. They're going to require more synaptic energy, so more neurotransmitter involved to stimulate that synaptic transmission, more vesicles, all of that stuff. It's going to need more stuff to recruit a larger motor unit because it has larger neurons, larger muscles, etc. Small neurons are going to be excited more easily. They're going to require lower input, and so we're going to recruit them first, right? And that just makes sense. It's more efficient for the body to call on a smaller motor unit that is easier to depolarize because the neuron is smaller. It's attached to a smaller number of fibers, right? This smaller motor unit only has 3 fibers attached. As we can see, the fibers here are smaller. The soma of this neuron will be smaller. The axon of this neuron will be smaller. So it's just more efficient for the body to recruit this one first. And if we need more force, we recruit a slightly larger one. If we need more force, we recruit a slightly larger one, et cetera, and recruit the very largest motor units at the last, okay? So again, thinking about me lifting something small or light or just my everyday movements, moving fingers, moving eyes, I'm really only going to be activating maybe motor unit X, maybe Y if it's a more strenuous activity. If I'm lifting at the gym, if I'm running, if I'm standing for a long time, I'm definitely going to be recruiting motor unit Z. All right. And as we can see at the bottom here, recruiting motor unit X alone provides X amount of tension, which is not very much. If I add Y onto the mix, Y has slightly more fibers, slightly bigger neurons, slightly bigger diameter of those fibers. So I'm going to generate more force. And then if I recruit motor unit Z, I'm definitely going to get a lot of force, right? I've got much bigger fibers here, a much bigger neuron here, and much more fibers attached to my neuron. Okay. What we'll look at lastly here is the velocity of shortening and how that changes with different types of loads. So when a muscle is contracting isotonically, in other words, the muscle is lifting or overcoming the load. Remember, isotonic means same tension. In other words, we are overcoming the load at that tension. The velocity is going to change. A couple other things are going to change as well. So the latent period of shortening is going to increase when the load increases. And that makes sense. We talk about the latent period as being the time that it takes to warm up the machinery to produce the cross-bridge cycling, to produce the tension. So if I'm lifting a heavier load, I'm going to need more of a latent period to warm up more machinery, to get more calcium going, to get more cross-bridge cycling going, to generate more force, right? The latent period of shortening is going to get longer or increase as my load gets heavier. The second point here is that the duration of shortening is going to decrease as the load increases. And that also makes sense. If I'm lifting an empty box, I can hold it up for longer than I can lift a box that is full of books or heavy objects, right? So the time with which I can keep that contraction going, the duration of shortening, is going to decrease as the load gets heavier, right? And then the third example here is the velocity of shortening decreases with the increasing load. And the velocity of shortening is how quick that muscle can contract. And so that is going to be, that's going to decrease, in other words, get slower. It's going to take more time to lift a heavier load than it will to lift a lighter load. So if I'm lifting a piece of paper, I can do that relatively quickly, right? The velocity here is very high. If I'm lifting a full box of books, the velocity is going to be very low. It's going to be very slow because it's going to have a lower velocity of shortening for a heavier load and a higher velocity of shortening for a lighter load. All right. So the rate of change, the distance is shortened. When the load is greater, we have the lowest velocity of shortening. So on this end of our curve, when the load is the greatest, the velocity is going to be the lowest, excuse me. The load is heaviest, the velocity is the lowest until the velocity gets to 0. And that is when the load is too heavy to be overcome and the velocity is 0, right? You obviously cannot lift that object if it is too heavy. On the other end of our curve, when the load is 0, right? If we're lifting a very light or weightless object, our velocity is going to be at its very highest, which is going to be the maximum velocity of shortening. Okay, this curve just kind of summarizes all of that and illustrates that here nicely. So let's compare and contrast lifting a very heavy load. If I'm lifting a very heavy load, the curve here in red is going to show what my distance shortened versus time would look like. So the first thing that we can appreciate is that the latent time increases. So the time between the stimulation and the actual shortening is going to be increased, right? So the curve is going to be all the way out here because the latent period has increased for a heavier load. The duration of shortening is going to be decreased. In other words, I'm not going to be able to sustain that contraction for very long because it is a heavier load. And so the width of this curve is much smaller than the other curves of lighter loads. And then the third thing here is the velocity of shortening. And the velocity of shortening is the slope of our curve. And as we can see, it is not as steep for the heavier load because it is going to take more time to actually lift a heavier load than it would to lift a lighter load. As we can see here, when the load is 0, the curve is very steep. We can do that very quickly because it's less machinery to be warmed up, and we can contract that muscle with more of a quickness, right? The velocity of contraction is shorter for a lighter load and is longer for a heavier load. And then looking at a zero load object, again, we have zero latent time. So we can lift a piece of paper with no latent period at all, less time to generate smaller amounts of force. We have a steeper curve in terms of the velocity of shortening. We can do that very quickly. And then we have a longer duration of contraction. So I can stand here probably all day if you asked me to, holding up this piece of paper, because it's such a weightless object. I could not do that with a heavier load because the duration of contraction would be much shorter for heavier loads.